Well, it's just at 12 noon. Why don't we get started? Because I know that we have a lot that Ahmed wants to tell us about cost effectiveness and using data. And if folks are having any technical difficulties, please do let us know. I think best is to either use the chat function, which I know Kari is keeping an eye on, or sending Kari an email. But I just want to welcome everybody to this, our second webinar. So my name is Andrew Pinto, and I'm a physician and scientist at St. Mike's Hospital in Toronto and connected to the University of Toronto. And with Richard Young, we are the co-chairs of the cost analysis group for that's really housed within the Committee for the Advancement of Science and Family Medicine, and we're part of and supported by NAPCREG. So we've decided this year to hold a few webinars that are to try to introduce to folks some ideas about cost effectiveness analysis. And we had a really wonderful webinar that was done in the spring by another colleague here, Juan Rudy, and that's actually available. If you didn't see it, you can listen to the YouTube video and of that recorded webinar. So today we're really fortunate to have Dr. Ahmed Bayoumi, who is a colleague of mine here at St. Mike's Hospital in Toronto. He is a scientist at the Center for Urban Health Solutions. He is a professor at the University of Toronto, connected to the Institute for Health Policy Management and Evaluation. And he holds a research chair here as well. And he's a past president for the Society for Medical Decision Making. And I had the great pleasure to complete my postdoc with Ahmed as my supervisor. So I will turn it over to him to talk a bit about introduction to the analysis of cost effectiveness data. Thanks.
Thanks very much, Andrew, and thank you everyone for the invitation and the opportunity to speak to this group. So what I wanted to do today was actually focus on how people who have data relating to costs and effects might think about analyzing that data. So I'm going to make this talk really focused to people who hopefully are wanting to do research, but I'm also not going to go into math in any degree. I'm not going to go into statistical programming to any degree. So I'm going to really show you, there might be a very tiny bit of math, but I'm really going to show you sort of what kinds of analyses people do, and then I'll give you some further resources at the end for those who are interested. So I'll just go back. My email is there and my Twitter handle, so feel free to contact me if you have any questions. I'm happy to answer those. So here's what I'm going to talk about. I'm going to sort of talk about how cost and effectiveness data might be structured and how we might actually get such data. I'm going to then talk about calculating and interpreting the incremental cost effectiveness ratio. And I know when Rita talked about that a little bit, I'm going to sort of review a little bit of what she did and then go a bit further. And then I'm going to really talk about how we try and estimate uncertainty around that incremental cost effectiveness ratio, which is somewhat tricky to do. I'm going to then talk about two methods that have been used to try and address some of the issues related to uncertainty. One is what are called cost effectiveness acceptability curves, and then very briefly I'm going to talk about value of information analysis. Both of those probably need a lot more depth, but this is really meant as a way of introduction to those topics. So let's start by thinking about cost and effectiveness data. So let's say that we have some data on costs and some data on health effects. And for the purpose of this example, I'm going to assume the costs are measured in dollars, and that health effects are measured in quality-adjusted life years, or QALYs. And that's QALYs are sort of a standard, commonly used measure for estimating health effects. And again, I'm not going to really go into what a quality is, but if you are interested, I can certainly send people resources if they contact me. And for most of the examples that we're going to talk about today, we're going to assume that we are just comparing two groups. Say that we have a control group and a treatment group. And again, if almost everything I'm going to say today does generalize to the situation where you might want to compare more than two groups, but some of the analyses do get a bit more complicated. But for our data set where we have costs and effects, and we have two groups, we're going to have a data set that looks something like what's on the next slide. So here I've shown you a listing from 10 people. So each row here is an individual, and you can see that there are three variables in this data set. There's a variable called cost, and let's see that that represents the cumulative costs for the individual in our study. So for the first person, they accrued costs of just over $451,000. The second person, $806,000, and so on. The second variable is the quality variable, and those are the cumulative qualities for that individual in our study. So person 2 accrues 6.2 qualities, person 1 accrues 6.2 qualities, person 2, 9.4 qualities, and so on. So, and then the third variable is a variable that indicates whether the person was a control or received a control intervention or the treatment intervention. And here I've just coded treat equals 1, meaning they received treatment, and treat equals 0 as meaning that they received a control. So one of the nice things about this data set is that it's entirely made up. And the reason that that's nice is because I can share it with you, and you can download and you can play with this data, and you can try and replicate the analyses that I'm going to show you. And I'm going to tell you in the very last slide of this presentation how you can go about doing that. This data and the examples that I'm going to show you is in Stata format, and the programs that I've written to analyze it data are in Stata format. I do apologize in advance to people who use other software, but it's fairly straightforward to generalize this. And I've also included two files that you can download. One is a series of custom-written programs that you can do these analyses. So you can do them fairly simply, usually by entering a single line into the software program. And the second is a file that you can run to replicate all the analyses and graphs that I'm going to show you here today. So please do feel free to download these and play with them. And if you do find any bugs, please do let me know about that as well. So I've shown you this data, but we might take a step back and just ask, how would we actually go about getting such data? And in general, health economists use two ways, I think, to get such data. They either collect them from individual patients or they simulate them. And the individual data could be collected within the context of a clinical trial. So many clinical trials now are doing economic evaluations alongside the trials. Or it could be observational data, such as from a cohort study or from an administrative data set, where it's possible to generate both a cost and a measure of health effect. Many of us use simulation models, and in general, and we'll talk a bit more about that, but those models might simulate data from individual patients, or they might simulate cohorts of patients. So if we're talking about clinical trial data, as I said, we would collect costs and health data within the context of a trial, and usually that would be a randomized and controlled trial. The great advantage of this, of course, as with all clinical trial data, is that there is minimal bias in the data. The differences in the both costs and the effects should ideally be only due to the question about who received the treatment or not. But there are some disadvantages to clinical trial data. So the people who are in trials are often different than the people to whom we want to apply the intervention. So there are questions about generalizability. And particularly for economic evaluation, there's a question of the time horizon. So this might be particularly important for cost data because costs don't necessarily accumulate at the same rate as health effects. So for example, if we were looking at life-saving surgery, there might be short-term costs, so that might be captured in the context of the trial. But clearly, the long-term costs and the long-term health effects are going to differ between those people that live and those people that die. So one of the significant issues in analyzing clinical trial data is this question: is the time horizon for the decision based on cost effectiveness analysis the same as the time horizon that the trial used to collect their data? And if it's not, then we often have to extrapolate that data, often using simulation methods. We could have observational data. That data is often more readily available and often has longer time horizons than the clinical trials. But the data, of course, are prone to biases. The treatment is often confounded with other covariates. And some very smart people have developed methods to adjust the economic analyses to try and control for some of these confounders. And I believe the next webinar is scheduled to be presented by Dr. Jeffrey Hodge, who is a friend and colleague of mine. And I think he's developed actually some of these methods. And so I'm going to leave further discussion of this for him to talk about at the next webinar. And then we could have simulated or model data. And one of the advantages of modeling is that we can really now explore a wide range of possible interventions, look at several different populations, look at different scenarios. We can also analyze potentially very long time horizons if we're comfortable extrapolating. That's both an advantage and a disadvantage. Because we now are simulating data and we're making assumptions and extrapolations, the validity is always in question. So there's been a fair bit of discussion about how we know whether a model is believable or not, whether it's valid. And again, I'll give you some resources. I'm not going to talk more about that now. But modeling is used very frequently in economic analyses. Sometimes models get very complex. And occasionally, and I've been guilty of this, the models may be so complex that the methods are somewhat opaque, even to reviewers. And so it can be challenging sometimes to assess model quality when models are very complex. And then there's always a concern that models are prone to manipulation, by which I mean, because they are simulations, the concern is that whoever is building the model might structure the model so that it gives the desired answer. So this again has been a topic of significant discussion in the literature, and you'll see, for example, that some very prominent journals will not accept modeling studies where the sponsor of that study is a manufacturer because of this concern about manipulation. Nevertheless, there are very many different approaches to modeling, and I think the important principle is that the model should be fit to purpose, by which people mean that the model should account for the most important aspects of the condition that is being modeled. So let's look at some examples. So if we had a condition where there were few costs and health effects and the decision was being made over the short term, we might be able to use a simple decision tree. An example of that might be pain relief for women in labor, where both the intervention has its effect over a short time horizon, the costs are over a short time horizon, any adverse effects are over a short time horizon, and so we can model that fairly easily. But we might also have a condition where there are long-term effects and people have multiple different health states and they keep transitioning between those health states. So if we were looking at hepatitis C, for example, we might want to model different stages of liver disease, including cirrhosis. We might want to model liver transplantation for people who develop hepatocellular carcinoma. We might want to model cure from hepatitis C for people who get treated. And so we really want to think about long-term health effects. And in that situation, we would ideally think about how to simulate an entire cohort of people. We might also, though, have long-term effects where there are multiple recurrent events. So if we're modeling osteoporotic fractures, for example, we might have a lot of differences between individuals in terms of how many fractures they get and which sites they fracture at. And so in that situation where where each individual has a different trajectory, we might want to do an individual level simulation, or what's often called a micro simulation. We also might want to think about models where disease transmission between individuals is important. So that might be important, for example, for HIV prevention, or really for any infectious diseases. Certainly for Zika, for example, we might want to model how the disease is spread between individuals, both through mosquitoes and through sexual contact. And in that case, we would want to use something like a dynamic compartmental model. And then we might also have interactions between individuals where the time to event is important. So we might think, for example, about a transplant waiting where somebody who gets on the waiting list and takes the next available organ might have an effect on the next person who's in line in terms of the availability of organs for them. So in that case, we would look to something like a discrete event simulation. So the purpose, sorry, again, just one more last comment about this slide. The purpose really is to say that there's no single type of model that's necessarily best. The type of model really has to be appropriate for the question that's being asked. So another point is that when we analyze the data, we really care about mean costs and mean effects. So the data that I showed you is at an individual level. Cohort data wouldn't look like that. Cohort data would just give us an overall estimate of the mean cost and mean effect, by which I mean the results of the cohort simulation model. But it is those means that we care about. And just to recap, then we could have trial data. We would summarize that data. We would get an estimate of mean costs and mean effects. We could have observational data, and we could do some fancy statistical adjustment, but we still end up with the mean costs and mean effects. We could have a simulation model that's at an individual level, and again, we would then summarize to get mean costs and mean effects, or we could do a cohort model, which would directly give us an estimate of the mean costs and mean effects. But in each of those examples, we end up with the mean costs and mean effects. And this is the important point. Once we have an estimate of the mean costs and mean effects, the way that we analyze the data doesn't change. So for the rest of the talk, I'm really going to focus on this idea of how we analyze mean costs and mean effects, regardless really of how we obtained those data. So let's move on to talk about calculating and interpreting the incremental cost effectiveness ratio. So we're going to go back to our data set, the data set that I showed you before. And so now I've summarized this data in a table. So you can see we have two groups, group 0 and group 1. And group 0 represents the control group, group 1 represents the treatment group. And for each of those groups, we can estimate the mean costs and we can estimate the mean qualities. And we can also estimate the standard error for both of those. And you can see that in the example I've shown you, group 1 accrues on average higher costs, but also higher qualities than group 0. And we can now calculate both the incremental cost and incremental quality. And really, these are just the mean and standard error of the difference in costs and the difference in qualities between the groups. And then by dividing the incremental cost by the incremental quality, we get the incremental cost effectiveness ratio, which economists like to call the ICER. So here the ICER is this $337,000 divided by this 0.4744 qualities, and that gives a ICER of $71,000 and $187.54 per quality. So that's our incremental cost effectiveness ratio, and I think Rudy covered that, so I've gone fairly quickly over this slide. But one thing I do want to point out here is that there's no standard error calculated for the ICER, and because it's a little more complicated than just calculating the standard error for the incremental cost or the incremental quality. So we have that ICER of $71,000 and change per quality, but how do we know if that represents good value for money? So one of the basic rules of interpreting cost effectiveness estimates is that they really are only interpretable relative to a threshold. So if we were willing to pay $100,000 per quality, then that $71,000 per quality would represent good value for money. And I think, again, when Rudy said some of this, I'm going to go fairly quickly over this point. Another way of saying that it's good value for money is saying that it's cost effective. Alternatively, if the threshold was $50,000 per quality, then the treatment would not be cost effective because 71,000 is greater than 50,000. Well, so I said just now that we can only interpret ICERs relative to a threshold, and so you might come back and ask me, well, what is the threshold? And there's a large body of literature on how to ascertain what the threshold is, or what it should be, and how to measure that. Much of this remains controversial. And again, without going into a lot of detail, common practice is to report thresholds of 50,000 or 100,000, or to report both thresholds. There was a opinion piece in the New England Journal of Medicine a year or two ago, which suggested that the threshold for the United States should now be $100,000 per quality. In Canada, we often still use $50,000 per quality. So, and then I think when Rudy also covered some of this, but it's also very helpful to look at costs and effects on the cost effectiveness plane. And the cost effectiveness plane is a graph. And here I've shown you the x-axis being the incremental effect, and the y-axis being the incremental cost. So again, we're important to recognize that I'm talking here about incremental. So I'm not focusing on the mean cost and mean effects of each individual intervention. I'm here focusing on the incremental costs and the incremental effects. And I've plotted here the mean incremental cost and the mean incremental effect. And if we draw a slope from the origin to that point, which is this dotted line here, the slope of that line will be equal to the incremental cost effectiveness ratio of $71,000 per quality. So this is really the same data that I showed you in tabular format, but now in graphical format. It is important if you're reading the literature to note that some people flip the axes. So some people put costs on the which of these is better, but you should recognize that you might have to adjust how you're looking at graphs depending on where that graph is coming from. There tends to be some geographic distribution in terms of how people do their axes. So just like I said, we can plot the incremental cost to access ratio with that, remember that dotted line in the last graph. We can also plot a line that represents the threshold. So here I drew a line, and you can see here that this line starts at the origin, and it passes through a point where the incremental cost is $50,000 and the incremental effect is 1 quality. So this line would represent a threshold of $50,000 per quality. And so this line really now divides this plane into two. So the points that are to the east and to the south of this line now represent interventions that are cost effective, meaning that any slope from the origin to any point here would have a slope or an ICER that's less than $50,000 per quality. Conversely, points to the north and west of the threshold represent interventions that are not cost effective. And so here again is our example. Remember, our green dot is our estimate of incremental costs and incremental effects. Our dotted line is our estimate of the incremental cost effectiveness ratio. And we can see that if the threshold is $50,000 per quality, which is this blue line, we would not be cost effective because we are to the northwest of this line. If our threshold is $100,000 per quality, which is this red line, we are cost effective because we are to the southeast of this red line.
So just something that folks may wondering, which maybe Ahmed can answer while he has this graph up, is what is the benefit of graphing this? And like, what would people take away from this graph? Like, what does it tell us more than just the number of what your ICER is?
So maybe I'll ask you to hold on to that question because we're going to talk a lot more about graphical approaches in a minute.
Okay.
So the other important concept is what economists tend to call dominance. So what if our treatment, so far we've given you examples. I've given you an example where the treatment has both a higher cost and has a higher effect. But it might be the case where our treatment is less costly and more effective than controls. And we would never choose the control in this situation, no matter what the threshold. So in this case, the treatment is said to dominate over the control. And this is sometimes called strict dominance. So there is another kind of dominance, and this one is called extended dominance. And this one is a little trickier, not much trickier, but a little trickier to think about. So extended dominance is important to consider when we're comparing more than two options. So we're going to step back from the example that we've been using for a minute just to explain this concept. So an intervention is extendedly dominated by another option if the incremental cost-benefit ratio relative to the next most effective option is greater than the ICER for another more effective option. That's a lot of words, but let me show you what I mean by an example. So let's say we're comparing 5 treatments, and we made this pretty simple. Just called, sorry, it's actually 6 treatments here, A, B, C, D, E, and F, each of which has a cost and each of which has an effect. And again, the cost could be in dollars, the effect could be in life years or qualities. It doesn't really matter. So let's go see how we would go about analyzing these data. So the first step is that we're going to sort these based on effectiveness. And we're also going to include no effect. So no effect is going to have 0 cost and 0 effect. And you can see here, again, these are the same 6 interventions, A to F, but now I've sorted them in order from the least effective to the most effective. And I've included the 7th intervention, which I'm just calling O, which has 0 cost and 0 effects. The next thing we're going to do is we're going to identify and eliminate any dominant interventions. So again, this is the same interventions with cost and effects. But if we look down here, we see that intervention E is more costly than intervention D, and it's less effective than intervention D. So we would never choose intervention D. If a rational decision maker in choosing between E and D would always choose D. You get more effect for less money. So we can eliminate intervention D from our portfolio of interventions that we're considering, and because of this comparison of E to D. In other words, we're saying that E is dominated by D. So we're going to drop E. So now here are that same graph, but now I've dropped E, the costs and effects, and now I've calculated the ICERs. And these ICERs are taking each intervention in turn, calculating the incremental cost and the incremental effects, and then dividing. So this would be the incremental cost between B and O is 100,000. The incremental effect is 10, so we get an ICER of 10,000. Between D and B, there's another 100,000, and then there's another gain of 3 qualities. 100,000 divided by 3 gives us 33,000, and so on. And so the ICER is it's important to recognize each ICER is comparing the intervention to the next in the list. And now if we look down this list, we can see that A at 50,000 has versus C has an incremental cost effectiveness that is higher than C versus F. Right? It's 50,000 versus 16,000. So although it's not eliminated by strict dominance, it is now going to be eliminated by extended dominance. And so we're going to drop A from this list. We really want a list in which the ICERs are increasing order. We don't want these funny ups and downs. And then, so we dropped A from the list, and now we're going to recalculate the ICERs. And we can see once we drop A, we again have this situation where we go 10, 33, but then we go back down to 16 and then up to 100,000. So we again are going to identify intervention D that is going to be eliminated by extended dominance. So we're going to drop D from the list. And finally, we're going to end up with the interventions that remain and ICERs that are strictly increasing. And how would we know which one to choose? Now, this is again where we go back to our threshold. If our threshold is $50,000, we would go down this list until we get to an ICER that is not greater than $50,000, so we would choose C. If we were willing to pay $100,000, we would choose F because its ICER is just at $100,000. So that was really to show you what we mean by dominance and extended dominance. And to get back to one part of the answer to Andrew's question, is that we can also, sometimes it's actually easier to see that graphically. So here I've taken those same 6 interventions as well as the origin, and I've graphed them on a curve. Now, note here that these are not incremental costs or incremental effects. These are the actual costs and effects of each therapy. So this is slightly different than the graph I showed you before. We can see here that E is to the northeast of D. And remember, we said northeast means not cost effective. Northwest, that should be, is not cost effective, and southeast is cost effective. But here, E is more costly and less effective than D, so it's going to be dominated. And then remember we said that D and A were extendedly dominated. And if you imagine in your mind a line that goes from B to C, you can see that that A and D are going to be to the northwest of a line that connects B and C. And I can actually draw that line for you, so it's easier for you to see. Again, anything up here to the northwest is not cost effective. And in fact, we can draw a line for all of the non-dominated interventions. And this now becomes what economists call the cost effectiveness frontier. So in other words, interventions that are on the frontier are those that should be considered under a setting of cost effectiveness. So remember I told you about the threshold and that different countries debate about what the threshold is. Of interest, some countries like Germany, that should be, focus on the frontier rather than on threshold when deciding which interventions to fund. So they say, if the threshold represents those interventions that are efficient, then they focus on, for each disease, trying to just ascertain what the most efficient treatment is rather than applying it relative to a single threshold that applies across all diseases. So, so far we've only talked about ICERs in the northeast quadrant. In other words, where there's the costs and effects are both positive. So interventions that are both more costly and more effective than the control. And we said we have to interpret these ICERs relative to a threshold value. Well, what about the other quadrants? So again, as I said, we've been up here, but we could have interventions that are less costly and more effective. And of course, if that was the case, if we saved money and improved health, we would say that this dominates control, and that would be easy, we would adopt. And what about in the northwest quadrant? Well, we could have interventions that are more costly and less effective, which now are dominated by the control, and we would not adopt. This would not be a good way to spend our money. And what about if we have interventions that both saved money, but we sacrificed health? Well, now again, that decision is going to depend on what the threshold is. So if we saved a whole lot of money, but we're willing to sacrifice a little bit of health, we might adopt that. Conversely, if we sacrificed a whole lot of health, but saved only a little bit of money, we probably wouldn't. So again, decisions in this quadrant really depend on what our cost effectiveness threshold is. So if we draw a threshold here, and I haven't specified what it is, but just like we said, there were points in the southeast versus northwest, we can draw a line that effectively divides the cost effectiveness plane into two. And we call this the willingness to pay line, indicating the willingness to pay threshold. And as shown here, anything in the southeast in the green triangle here represents good value for money, and things in red represent poor value for money. So this is going to be important when we come to think about uncertainty around the ICER estimates. So point about negative ICERs. An ICER can be negative because it's in the southeast quadrant, which is, remember we said was really good because it saved money, even though it improved health, or it could be negative because it's in the northwest quadrant, which is really bad because now we are spending money and we're getting worse health. So negative ICERs can be really tricky to interpret because it depends which quadrant they're in. Negative ICERs are also hard to interpret. They don't, economists like to say they're not well ordered. And let me give you an example to show what that means. So let's say we had an intervention that saved $50,000 and gained 1 QALY. So the ICER would be negative 50,000. And we had another intervention that saved $100,000 but gained 2 QALYs. So clearly we would like to save more money and get more health effects. So we would choose the second one over the first one. But both of these have an ICER of negative $50,000 per QALY. And so that's just one example, but there are other examples, and again, I haven't gone into it here in detail, to show that negative ICERs really don't have much in the way of interpretation. The bottom line here really is don't report negative ICERs. They should be reported as cost saving or as dominated, but not as the numeric value itself, because the numeric value really doesn't have much intuitive meaning. Okay, let's move now to talking about estimating uncertainty around the incremental cost effectiveness ratio. So far, we focused on estimating and interpreting the mean ICER, but like any other statistic, we may also want to estimate the uncertainty that's associated with the ICER. And two methods that have been used, two numeric methods, are called, one is the delta method, and the second is Feiler's theorem. And here I've shown you some results when the computer is asked to calculate the uncertainty. So I've shown you the lower and the upper 95% confidence intervals. And I'm not going to say much about the delta except to say don't use it. So I've included it actually in the statistical program that I wrote, but there are many reasons why it's not a good measure, particularly for cost effectiveness estimates. And I've shown you the bounds that are reported by Feiler. You can see here that the lower bound is negative. So although the computer will calculate a negative confidence interval, we just talked about negative ICERs. So if we look at where this is likely to be, we can see that because the upper bound is greater than the ICER, we can infer that this is in the southeast quadrant. In other words, it's cost saving. So I suggest if you get a result like this, reporting it as the 95% confidence interval as being anywhere from cost saving up to $143,000 and $143,081 per QALY. So another way to estimate the uncertainty around the intervals is to use bootstrapping. And generally, bootstrapping is preferred over the other methods. And in brief, if there are NT people who receive the treatment and NC people in the control group, we randomly sample NT and NC people. We calculate the incremental cost, the incremental effect, and the incremental cost effectiveness ratio. And we repeat this many times. How many is many? Well, it's some people say 1,000, some people say 5,000. It really depends on how many replications it takes to get stable estimates. For somewhat complex reasons, they can sometimes yield biased results, and there are some biased correction methods that have been proposed. So here I've shown you the last 3 rows in this table are estimates that are based on 5,000 bootstrapped samples one using what's called the percentile methods, and then a bias-corrected method, and a bias-corrected and accelerated method. And people who have studied this said that the bias-corrected and accelerated probably gives the best estimate of the true 95% confidence interval. And if you look, you'll see that the Feiler estimates and the bias-corrected and accelerated estimates are pretty close, actually, to each other. And in general, as a rule of thumb, when the estimates are in a single quadrant of the cost effectiveness plane, or most of the estimates are in a single quadrant, the Feiler and the Bootstrap methods often are actually pretty similar. So a few notes. If we're using simulation modeling, probabilistic sensitivity analysis like Monte Carlo approaches will yield many estimates of costs and effects, and these can be analyzed the same way as we have analyzed the Bootstrap. But note, we want the mean costs and mean effects over all repetitions. We don't want an average of the mean ICERs. So we'd calculate, if we had 5,000 estimates, we'd calculate the mean cost, if we calculate the mean effects, and then divide those two. We wouldn't calculate the mean ICER for each one, and then average the ICERs. So going back to our graphic representation, so now the red dot here represents our mean costs and mean effects, and each green, very small green dot here represents one bootstrapped sample of our estimated mean cost and mean effects. And you can see I've produced 5,000 samples here on this plane. And most of these are in this northeast quadrant, but you can see that there are some down here in the southeast quadrant, some in the northwest, and even very few in the southwest quadrant. And now we can actually graph those results that we got from the bootstrap samples. So here, this is using previously called the percentile method. And so this, again, is another way to think about 95% confidence intervals. And what does this really mean? It would mean that 95% of the bootstrap samples are now between these two red lines. And 2.5% would be below the bottom line, and 2.5% would be, above the top line. So this is a pretty convenient way to think about bootstrapping, to think about what bootstrapping and what the confidence intervals actually are. And here I've just shown you, remember that table that I showed you a few slides ago that showed you the confidence intervals by different approaches. And here you can see that I've graphed them, and you can see that they give pretty similar results. There are, however, some problems with the confidence interval approach. So what I haven't actually showed you is that we need to rank the estimates both by quadrant and by the ICER. We don't want, if we just listed the ICERs from negative to positive, we would be listing those both in the good southeast quadrant and that really bad northwest quadrant. Also, the confidence intervals aren't defined when the ICER and the that should be the mean cost and the mean quality are both close to 0. And furthermore, the ICER can blow up really high because it's a ratio when the mean effect is close to 0. So when we're dividing by a number close to 0, we get some astronomically high numbers that are really hard to interpret. So for all of those reasons, reporting confidence intervals around ICERs can sometimes be impossible, and at other times can give results that are a little bit weird. And so people took a step back and said, well, what do we really want to know? Why do we want to know about the uncertainty around the ICER? And so that led people to develop cost-effectiveness acceptability curves. So if we go back to this graph, recall this line where we said we could divide the willingness to pay line, divide the cost-effectiveness plane into two regions by willingness to pay line. Now, if we apply that again to our bootstrap samples, and I've shown you the bootstrap samples, and I've drawn a willingness to pay line, and you can see down here by the legend that the willingness to pay line is for $50,000 per quality. And now we can count, and remember we said anything to the southeast is good, and to the northeast is bad. So we could count, or we could actually have a computer count, how many of these dots are below this line and how many of these dots are above this line. And when we do that, the computer tells us that 22.9% of the points are southeast of this line. In other words, that they're cost effective. And then we could repeat that at different thresholds. We could actually do it if the threshold was 0, in which case we see 3.5% are south of this line. We could do it if the threshold was $1,000, in which case we get 85.6%. We could do it at a threshold of $150,000, in which case almost all, 97.7%, are to the southeast of this line. And we could do it, so that should be 200,000, in which case now we're getting to 99.2%. And then we can actually, so now we have different willingness to pay thresholds and different proportions of that represent cost effectiveness. And we could graph those. So we can graph the probability of cost effectiveness at different willingness to pay thresholds. So if these are the willingness to pay thresholds and these are the probabilities of cost effectiveness, we can graph one against the other. And that's really what the cost effectiveness acceptability curve is. So actually, let me show you the curve and then come back to this slide. So here's what it looks like. So again, we said that at $50,000 per quality, we had, 22.9%, just about 23% of the points below this line. And if we go back to the curve, we can see at $50,000, we're going to have about 0.23 probability of cost effectiveness. At $200,000, we're very close to 99%, and so on. So we just take each of those points and we graph them, and we get a cost-effectiveness acceptability curve. So a few points about this. This is not a cumulative distribution function, so it looks like a cumulative distribution function, but for many reasons it's not, and I've given you some resources that explain that in more detail. It doesn't necessarily start at 0, and it doesn't necessarily end at 1. We can also generate cost acceptability curves when we're comparing more than 2 interventions, but as I've said, that does tend to get more complicated, and you should really do some extra reading if you're going to do that. And particularly, in the last couple of years, people started talking about cost effectiveness acceptability frontier, CEAC graphs, and I haven't gone into those, but I've given you a reference for those. And those are particularly important if you're comparing more than 2 interventions. And finally, let's talk about value of information. So again, this goes back to the question, why do we care about uncertainty? What are we actually going to do with our estimates of uncertainty? So one reason is to determine whether it's worthwhile to invest resources to try and decrease our level of uncertainty. So that is, should we adopt our treatment or should we do more research? And we can calculate the expected value or the average value of acquiring additional information. And people use a shorthand term of value of information for this kind of analysis. And these calculations use our estimate of uncertainty. So again, I'm going to really just give some introductory remarks about this because it's worth an entire lecture or two on its own. But people started this sort of thinking by saying, what if we had perfect information? So what if we had no uncertainty about model parameters? And we call this the expected value of perfect information, or the EVPI. It's also possible, but it gets more complicated, to calculate the partial EVPI, which is really the expected value for perfect information for only some parameters in the model. The expected value of sample information, so that would directly address, because we don't really get perfect information by doing another trial. We get new sample information. So that would more directly address the question of whether it's worthwhile to do a clinical trial or collect more data in other ways. And we could also do a partial EVSI that addresses the question of whether it's cost effective to do more research that's targeted to specific parameters, perhaps the utilities or perhaps the costs or some issue related to survival, but we might focus on collecting better data on some parameters over others. Each of these is progressively more complicated. I'm only going to talk about EVPI today, and I'm really just going to show you an EVPI graph. And they tend to look something like this. So on the x-axis is the willingness to pay threshold, and on the y-axis is the expected value of perfect information. And what this curve represents is the maximum amount that a decision maker would pay for additional research per person to get perfect information. So if the willingness to pay was $50,000, the expected value of information would be somewhere less than $2,000. And at $100,000, the expected value of perfect information is $957. So that's how much we would be willing to pay per person to get perfect information on all the parameters. In other words, to reduce all of the uncertainty around each parameter in our model to 0. So the maximum EVPI is at the mean ICER. Remember, our mean ICER was $71,000, and that's where this curve reaches its peak. And that's because below that, we would choose one intervention. Above that, we would choose another intervention. But it's at that peak where we're really the most uncertain about whether treatment is better or worse than control. So what I've shown you is the per person EVPI. Usually, what we want is the population level EVPI. And so it's the same sort of calculation, but now we want to include things like how prevalent the disease is, the time frame of the decision, the discount rate for the decision, and then we can calculate a similar curve. And I haven't shown you here just because of time, but if you download the resources, you can see how to calculate that. So EVPI is useful if the cost of research is above this value. So in other words, if that's how much we're willing to pay for perfect information and research costs even more for that, then it wouldn't be worthwhile to do the research. We should just go ahead and adopt the intervention. But more detailed analyses like the expected value of sample information or partial sample information are required if the cost of research is below the EVPI. So just a couple of summary slides. First, I've said all of this, but let me just reiterate what are some pitfalls to avoid. So don't report negative ICERs. Instead, report whether it's intervention is dominant or dominated. Focus on the mean cost divided by the mean effects, not the mean of cost effectiveness ratios. Analyze data for multiple interventions using the rules of strict and extended dominance. There was a paper even in the Lancet a couple of years ago that did not do that, and there were lots of letters to the editor afterwards. You'll see people talk about the delta method, but really the delta method shouldn't be used to calculate uncertainty around cost effectiveness ratios anymore. Be cautious about other methods to report confidence intervals for ICERs, particularly if you have bootstrap samples that go into multiple quadrants. Graphical methods like cost effectiveness acceptable curves are often preferable over numeric methods. And don't interpret cost effectiveness acceptable curves as cumulative distribution functions. They are something more complicated than that. And the key learning points, we care about mean costs and mean effects, whether that's from individual data or from model data. Cost effectiveness ratios have to be interpreted relative to the direction of the cost and effects, in other words, the quadrant on the cost effective planes, and relative to a threshold. That threshold might change, or will change from country to country. Bootstrapping or simulation modeling are probably the best and most effective ways to estimate uncertainty. Cost effectiveness curves and value of information analysis are also good ways to express uncertainty. Things get more complicated when considering more than 2 interventions. So if you have that sort of situation, you will need to do more than what I've talked about today. So I will share these slides, share some places to go for more information. And on the last slide here, just some instructions for people who use data in terms of how you can actually download the sample data set and the programs that I use to create all the tables and graphs that I've shown you in this presentation.
That's wonderful. Thank you so much, Ahmed. And we have about 5 minutes for questions that people may have. So I believe we have a function that people can use to write in questions on the system, and guess I'll ask one question for you, Ahmed, that comes to mind, particularly for people who are just getting started in this area. Could you tell us a little bit about one of the graphs that you showed, which was the bootstrap replications that were done around that? Is that has that become sort of the standard approach to looking at estimating confidence? Because from what you indicate, it seemed like it was preferred over other sort of methods. But has that sort of become the standard?
Yeah, if you're going to estimate confidence intervals, then bootstrapping is probably the best way to do that. But more and more people are moving away from reporting confidence intervals to reporting cost-effective accessibility curves and sort of key points on that curve. So the probability that an intervention is cost-effective at $50,000 or $100,000 per quality threshold.
Because I'm anticipating some of the folks who are joining us, what they would be at the point of is when they're designing a study, and want to include an economic evaluation, to include within, say, a grant application or their protocol that they would collect this data on effectiveness, of course, but then also cost, and that then some ideas about how they would analyze it. So this actually gives us some of the language that would help us with doing that initial. Any other questions from folks on the line or calling into the webinar?
Yeah, hey, this is Richard Young. I guess I have a basic question. You use data to calculate all your results there. Can you talk about, can you do this on some of the other common programs, SPSS or SAS? And then what about other software that's available for people to do this?
So you can certainly do this. None of these complications are particularly tricky. The benefit of using a standard statistical program like Stata or SAS or R is that they have those bootstrap routines already built in. So you don't have to write the bootstrapping algorithm yourself. You can just call the bootstrapping algorithm that's there. I don't know if anybody has written the code to simplify this, but if you look at the Stata code, most of the Stata code that is there isn't that complicated, with a couple of exceptions. So you could, you'd have to know a little bit of programming if you wanted to write similar macros, but you can always do these from scratch without too much difficulty.
And I'll say that I have nowhere near Ahmed's experience of this, but I was able to, with some help, do the bootstrapping for a simple study, and it was within Stata and wasn't too complicated. And there are actually, even doing it within Excel, there's some really excellent resources that you can find on doing bootstrap replication. I think that
yeah, so somebody's asking more about the first seminar, and I think Kari said she's going to send out the link.
Yeah. And I think we are going to put the links to all of these webinars on the committee's website for future reference. And we'll, in our emails out to folks on our mailing list, we'll include both of these recordings, the links to both of these. So we're just at 1 o'clock. If there are no other questions, I'm just going to thank Ahmed on behalf of our committee. And I want to say this is also just a wonderful resource for us for the future too, that we can refer people to and as they want to learn more about this. And I also say, Ahmed, whenever he teaches, he's also just really amazing with giving people examples and data to much, Ahmed, for your time, and thanks everybody for joining us.
Thank you.